All right. So at the end of last lecture, I sort of just introduced the Axion a little bit. It was the very simple model where you add just the kinetic term, and then you add one term to the Lagrangian over f theta. It's 1 over 32 pi squared g tilde. So basically one new particle, one new coupling, and then what we did was we just said, well, look, A over f always appears with theta. So we just take all of our previous results, wherever you saw theta or what appears in the chiral Lagrangian will be theta bar, which is just equal to theta plus some other stuff. You just replace it with that plus A over f. And so this meant that, for example, that the potential of the Axion was something we had derived in the first day, but in particular that it had a minimum of at theta bar equals 0, 1/2 theta bar plus A over f. And in particular, the neutron EDM vanishes at the minimum. And so what the Axion does is it dynamically sets the neutron EDM to 0. And so we claim victory over the strong CP problem. The first thing to note is how plausible is this guy, right? Having a single new particle with this particular interaction. In particular, the way we write down theories is we postulate a bunch of symmetries. We say how everything transforms under a symmetry, and then we just write down every term consistent with the symmetries. And in particular, you'll notice that there's no symmetry that associated with this coupling here. There is something that we like to talk about, which is an anomalous symmetry. In particular, there is a fake symmetry where A goes to f plus alpha, and theta goes to theta minus alpha. But this is sort of a bookkeeping type thing to just tell us if we know how theta appears, how A must appear. This doesn't tell us, this is not a real symmetry, right? Because theta is just some number. And so you don't say the Yukawa coupling goes to 5 times the Yukawa coupling or things like that, or the mass of the up quark goes to 3 times the up quark mass. It's just some measured value. It's not going to, it can't transform under a symmetry. So how do we get a theory that actually looks like this? The answer is with much difficulty. Despite the fact that this is a very simple model, the models that give these guys have associated problems with them. So to see that, I'm going to just write down the simplest model to do this. And then we can sort of see why you would have some problems. So the first thing is the Axion starts off looking like, if you ignore this coupling, as just a free scalar. Yeah? Yes. There we go. That's right. Sorry. A goes to itself plus. Sorry. Yeah. Yep. Yeah. Now the dimensions work and everything's good. All right. Yeah. So the starting point is to take A as a pseudo-Goldstone boson. In particular, we're going to say we start with a theory, and there's a U1 symmetry under which phi transforms. So you have the standard phi squared, and then in your Lagrangian, let's see, I guess t minus v, so it's going to be plus m squared phi squared. Okay, so this is your Lagrangian. So this is t minus v, so you can see it has a negative mass squared. And so you get a VEV here. We're going to then expand phi as f plus some radial mode, just to make clear that this is a field. Then e to the I A over f, where A here is your Goldstone boson. So this is our first starting point. And then what we're going to do is couple this guy to some quarks, plus phi q bar, where q is just some quark that's just charged under SU3. It may or may not be charged under U1 or SU2. It doesn't matter. And if, for some reason or another, this happens to be the only way that these quarks get a mass, then what happens is you can see that this term, this mass term, turns into, let's integrate out the radial mode so we can forget it. It's just focus only on the Goldstone boson, e to the I a over f q bar. And now we can do a symmetry transformation. Well, field redefinition. It's not a symmetry. We'll redefine q prime equals q times e to the I a over f. OK, my e overlapped with my q, but oh well. And this is not a symmetry of the theory. In particular, it's an anomalous field redefinition. And so when you do this field redefinition, you now have you have your mass term, which is just f q prime q bar. So a nice mass term that has no coupling with anything. But because this is an anomalous symmetry, you get a over f 32 pi squared gg tilde. And so if you have this coupling, then you have in the EFT, after you've integrated out both the quarks and the radial mode, you have the axion. So this is sort of the simplest model of how you would get an axion. And it illustrates sort of one of the problems I just mentioned, which is that you'll notice that there's no reason why you can't just add a mass term here, m q bar. It's true if you don't write it, then you have the axion. But if you don't have it, or if but there's no symmetry reason why this term should not be there. In addition to this, there are actually a lot of other problems associated with this model. One of the most common one you'll hear people talk about is called the quality of the axion. So that's the statement that aside from fine-tuning this relevant operator to being very small, or just setting it to be very small, you also have to suppress a lot of higher dimensional operators. Since the U1 is not a good symmetry, right, because it's an anomalous symmetry. This means, so people familiar with this, global symmetries like what we're talking about are not respected by quantum gravity. And so people expect that higher dimensional operators suppressed by M-Planck should be breaking all these symmetries. If it's not a gauge symmetry, if it's just a global symmetry, it's not going to be a good symmetry. So you can write additional terms, right? We're effective field theorists, and our UV cutoff is at least M-Planck. M-Planck, so you can write phi to the fifth plus ... just the general term phi to the n over M-Planck to the n minus 4. OK, so why are these a problem? The reason why they're a problem is that because they don't respect the U1 symmetry, you'll notice that if you put in phi is f times e to the I a over f and add the Hermitian conjugate, right? We have to do that. That these turn into cosine potentials, right? Adding the Hermitian conjugate takes the real part. And the real part of this guy is just the cosine. Real part of an exponential is the cosine. And so, for example, if you just take an arbitrary term here, what you get is the real part of f to the n e to the I a n over f over M-Planck to the n minus 4. And so this is a f over M-Planck n minus 4 cosine n a over f. So you'll notice that, and let's say this coupling is a complex coupling. So I just wrote its absolute magnitude, but it'll have an additional phase. And let's call that phase phi, right? And so then this will have some coupling phi. And so you can see why this term is now dangerous. Because if this coupling here is large, then the expectation value of A over F is just tied to the phase of this higher dimensional operator and is not tied to the QCD axion, or the QCD phase that you're trying to get rid of, right? Because the neutron EDM is proportional to theta bar plus A over F. And so we need the VEV of A over F to be equal to minus theta bar up to 10 to the minus 10 in order to be a good solution to the strong CP problem. And another thing you'll notice is, well, I'll get to it later, but the preferred value of F people like to talk about is around 10 to the 11, 10 to the 12 GeV. So this number here is very large compared to m pi f pi square, which is of order 100 MeV quantity square to the fourth. So you can see that these terms can be very deadly. And so if you actually work out, say that you want, let's put f of 10 to the 12. If you want 10 to the 12 to the nth power over m Planck, so m Planck is 10 to the 18 GeV or so. So 10 to the 18 to the n minus 4, and then GeV to the fourth. Cosine n A over F plus phi. So if you want this minimum, the absolute minimum, to be smaller, to be within theta bar to 10 to the minus 10, then this guy has to be, the magnitude of this potential term has to be 10 to the minus 10 smaller than that. And so if you just work out what value of n do you have to take until this thing is smaller than 100 MeV to the quantity to the fourth, its n needs to be 14 or larger. So, yeah?
Sorry, not to make you backtrack hugely, and you might have said this, but I missed it. Looking at the potential term when you wrote top, so you've got like the Lagrangian term for the action,
Yeah.
where you've got a G tilde.
Yep.
And then you happen to need that this is your potential. And presumably that should be related to the second term, axion term in Lagrange.
Yes, that's right.
I don't see how, because the A dependence is fundamentally very different, and that looks like it means that the gluon field strength tensor is going to have to be A dependent, which is odd.
So the statement is, you'll notice that A over F always appears with theta here. And at the in the first lecture, we basically did not put in the axion and just studied QCD. And we found that the potential energy of QCD was this number here.
I remember you saying
And so because theta bar equals theta plus phases of the masses of the quarks, theta md, you can see that if you're just taking this guy here and taking everywhere you see theta, replace it with theta plus A over F, that what we had derived before now appears like this.
That part I follow. Just it looks to me like to get from point A to point B, you need to have theta and A dependence in your gluon field strength tilde tensor GG tilde.
No, because, well, it depends exactly what you mean. For example, this came about by calculating the expectation value of the pions. And so it is true that the expectation value of the pions is a function of your axion field now. And so what I did was essentially I integrated out the heavy degrees of freedom. And because the mass of A is very, very light, in particular, for example, you'll notice that let's calculate the mass of MA for an F, a preferred value of like 10 to the 12 GeV. This is 100 MeV quantity squared over 10 to the 12 GeV. And that is numerically, what, 10 to the minus 14 GeV. So that's about a micro EV.
Okay.
And so because MA scales as micro EV, well, at least for this particular value, it's much, much lighter than everything else. And so what you do is you just integrate out all of QCD and then just ask, what is the potential remaining for the axion? And so that's in principle what you're doing here. And then it's like, okay, is it coming from GG tilde? Is it coming from the pions? You've just sort of integrated that all out.
So the V of A is not actually directly direct reformation or whatever of the second term of that.
It's more than that because, for example, this depends on the masses of the quarks. And so it is not just this term that contributes to getting this potential. You have like the masses of the quarks and a lot of other things.
All right, thank you.
Yeah.
That's bothering me.
Yeah. Yeah, I should have said that earlier. But all right.
Can I ask a question about the drawing?
Yep.
You may have mentioned this. The term phi q bar is determined by like CQ1.
Yes.
Under renormalization group load, other terms don't show up with phi with U1 control.
Okay, so under RG evolution, if you set this small, let's say you set this to 0, RG evolution will not generate a mass term that looks like this.
But what about in terms of the potential, like just integrating out if you have the quark loop,
Ah.
for example? Yeah.
So you will get other terms. So actually, yeah, so this I was going to talk about anyway, so might as well just talk about now. The statement is the way the axion appears is completely determined by this shift symmetry, anomalous symmetry. So if you want any non-derivative couplings of the axion, you need to look for wherever theta appears. However, and theta only appears in perturbation in non-perturbative physics because GG tilde is a total derivative, and so theta never appears in perturbation theory. Or equivalently, you could just calculate all the Feynman diagrams here, and you'll see none of them depend on theta. However, derivative couplings are different. The reason for that is the derivative of a constant is 0. And so you could have a term that looks like it was never there. Like, for example, d mu a over f plus theta times, let's say, q gamma mu, q bar gamma mu q. So if you had no axion, this is the derivative of a constant, and this thing is just completely negligible. But once you have the axion there, you can just ignore that piece, and you get d mu a over f q bar gamma mu q. And these terms are generated by RG evolution. Yes. It's a dimension 5 term, but you're generating it from another dimension 5 term. Because a over f GG tilde is GG tilde is dimension 4. So when you multiply it by a over f, that's already a dimension 5 operator.
I guess I'm kind of confused. It looks like you brought down the Lagrangian of the potential where
Ah.
it usually appears, and that's all dimension 4. And then integrating out the longitudinal mode, I thought was what gives you then that dimension 5 operator.
Yeah, so when you integrate out this longitudinal mode, you can also generate terms like that. And even if it's 0 at tree level, it'll at loop level appear. And it turns out it is impossible to avoid having terms like this. The best you can do is say that they're about a loop factor smaller, and say they're generated by RG evolution. So it's like a loop factor times a log. The log can sometimes be large, so it might not be that much smaller. But yeah, you will always have these couplings. However, you will not necessarily always have the following couplings, which are a over f times ww tilde, or a over f times, we haven't broken electroweak symmetry, so let's call this bb tilde. So why don't you necessarily generate these guys? The reason is you can do plus theta weak over 32 pi squared ww tilde plus theta b over 32. And you can see that if you want this to be generated, it is not consistent with these shift symmetries here, where this theta is now really your theta gluons, since I'm multiple thetas. And so RG evolution cannot generate these two terms, even though these are sort of shift symmetric interactions. If you calculate Feynman diagrams with this, you always have a derivative on the axion. But because they're sort of topological and sort of tied to these theta parameters, this actually is never generated in RG evolution. So these sort of derivatives interactions are generated. These are not. Now, if these Qs had electroweak charge, then this field redefinition is anomalous under SU2, and you would generate this term, because then the real symmetry is not just theta G shifting, but also theta weak goes to theta weak minus alpha. And analogously, if these quarks have U1b charges, then again, this rotation is anomalous under U1b, and you generate this term. But you just generate it once, and then it just stays the same forever. Yeah.
I have two quick questions. I think they're related. When that first thing we're in the middle board, you've got the d mu a over f plus theta. Is that theta or theta bar?
It doesn't matter because it's a constant that just.
So like theta bar.
But in principle, I'd say you should write theta g, rather than theta bar. But because that's sort of when you first write down your Lagrangian, that's the symmetry you have. In practice, it doesn't really matter because you're taking the derivative of a constant.
Because the thing, if you can have, if the phase, for the mass phases can change, does that mean that what you, since the minimum, as I understand it, is that A equals negative f theta bar?
Yeah.
Does that mean that what you've got is A is kind of going to, or whatever, a dynamic minimum?
Yeah, so for example, if you're asking a question that's energy dependent, then this is some energy dependent quantity. And so yes, you would not oscillate exactly around there. In practice, the standard model, the changes in theta u and theta, the phases of the quarks is very small. And so in practice, it's a negligible effect, but in principle, yes, it's there.
Okay.
Yeah.
So in principle, if we had those couplings as well, could we get SU2 weak instantons also inducing one of those potentials?
Yeah, so you'd have U1 does not have instantons, so we don't care about that. SU2, yes, we do. But if you remember that the instantons are proportional to e to the I integral d4 x gg, or right, with some numbers out front. And when you calculate this, this goes to e to the minus, I think it's 8 pi squared over g weak squared times some numbers out front. And so it's just exponentially small. Okay. But in principle, yes, it's an effect that's there.
And would that tend to shift the Axion minimum away from that?
Correct.
Okay.
It's just numerically, it turns out to be something negligible, basically because we Higgs SU2, so it never gets strong. And so this G never goes to order 1 and becomes large, non-exponentially suppressed, which is what happens in QCD. So for example, you can ask, what about UV contributions to the mass here? Right? Then it's really G squared at some some higher RG scale, but it's exponentially suppressed, so it's subdominant to that guy there. But it does point out that these UV contributions are centered around theta bar at a different energy scale. And so in principle, if QCD, if theta bar, let's say, had some large running, and QCD became strong again at some other point in the UV, you get another point, another sort of mass term for the axion that would be very large, centered around some place completely different, and you'd screw up the solution. So it's true, the axion of the solutions, the axion is the most robust, but even it is not sort of immune to everything. Yeah.
Maybe I just misunderstood, but the argument used for the
Yeah. Yeah, it's going to have some mass at 10 to the 12 GeV or so. Yes. So that's sort of one of the unpleasantness about trying to get models of the simplest model of the Axion is this. Well, there is a mass term that's generated once you set it at its expectation value. And that's why you can integrate it out. It's just because the symmetry is broken, so then the mass term is generated. Yeah.
So how would that reintroduce the Axion coupled to standard model fermion? In some way it generates
Yeah, so essentially everything can generate these sorts of terms. It's very easy because there's, the symmetry that you have protecting the Axion doesn't protect this coupling. And so generically, whatever you do will generate these sorts of couplings. And so it's very unnatural to not have these couplings.
So would that also, because standard model are like, have SU2 that you want charges, that this coupling to standard model will further introduce the Axion WW?
Yeah, so it depends on just your arbitrary choice of the charges for these heavy quarks. The natural value is to probably be like, maybe they're like right-handed quarks or left-handed quarks, which then they definitely have B charge. They may or may not have W charge. But yeah, remember the B turns into the gamma and the Z boson, and so this would give a ZZ coupling and things like that. All right. Yes.
Here, our approach is that the corner or the AOF, the phi,
Yes.
we the other way, we corner the theta into the phi. We also see that.
So if you're saying that you're wondering what happens if I do a field redefinition to get rid of theta, what can happen is then you can also do a field redefinition to push A over F to the mass terms of the quarks. Because remember, the way we saw A over F appear here was by doing a field redefinition on the quarks, which then had it in the mass term, I guess here. So if you did a field redefinition moving theta to another place, you could also do a field redefinition moving A over F to follow it there, and then you'd still have that shift symmetry. Or equivalently, you can say, just write down the Lagrangian. Maybe you chose theta to be 0, but I'm still treating it as a parameter whose expectation value just happens to be 0, but still has this fake shift symmetry acting on it.
I see the shift symmetry part, but I don't see how we can get the same potential for theta bar.
So these additional terms appear because it doesn't just have those couplings. It's saying you might have additional couplings that are suppressed by gravity. And so the idea is just saying that how well you can actually make that EFT is limited. And it turns out that you have to suppress it to m Planck to the 10th power to make that a good EFT that looks like that. And so the statement is just really, it's hard to make an EFT that looks like the one we want. That's the statement. The EFT by itself solves all the problems. It's just that you can't make an EFT that looks like that well enough. At least not easily. Okay. Is that all the questions? All right. So the statement is to get an EFT that looks like that, you just need to suppress operators that are suppressed by m Planck to the 10th power, which sounds very difficult. So there are various tricks to get around it. In the interest of time, I guess I won't talk about them in detail, but I'm just going to very quickly sketch the sort of simplest four-dimensional way of doing it, which is just the statement that you know that pions have a coupling to the photons, pi 0 over f pi f tilde. And if you want to ask what are higher order corrections to sort of things like the pion potential, they would be things like q bar squared over mw squared, right? From there are higher order corrections to everything in the pion potential. One of them comes from integrating out the W bosons. Well, there are gamma mu's here. Oh well, you can't really see that, but there's a gamma mu in the middle since it's a gauge boson. And so what you see originally is that this turns into things like the derivatives of the pions. But because QQ bar has dimension 3, the higher dimensional operators you can write down are not just phi. You don't have to say it's phi to the 14th. Now it's just going to be something like QQ bar to the 5th or something like that to get analogously high dimension operator. And so if you make the axion a composite operator, sort of like the pion, you can sort of make these higher dimensional operators suppressed, because what they look like in the UV is really a product of quarks, and quark are fermions, and fermions have larger dimensions than scalars. And in fact, if you make the axion not just a product of 2 quarks, but a product of like 3 or 4 or 5, or you can say, or if you just say the product of 2 quarks is not gauge invariant, then just because you have a chiral theory, then you can get around these problems. But this is sort of a bit of a detail. Yeah. Yeah, so what they did, the first solution to get rid of these was imposing something like a Z14 symmetry and say the U1 symmetry is bad, but the Z14 symmetry is good. And then you can suppress those things. And that was literally the first solution to these problems, just imposing a like horrendously large and ugly discrete symmetry. Yeah. Mm-hmm. And this is just saying that sort of by making it composite, you can very naturally have these accidents where you need to write down many fermions in the UV to mimic this operator. Okay. So yeah, I don't think I have time to get into models, so let's not talk about this. And instead, I will hopefully have enough time to talk about why people really like the axion as dark matter. Because this is one of the appeals of the axion is, it is, as I said before, it is right now it's the best allowed solution to the strong CP problem, but it can also act as dark matter. And let me grab notes. And these, and in fact, it behaves as a very good dark matter. And so that's really one of its huge appeals. So let's go through how to estimate why it can be dark matter and how you might estimate what its abundance is back of the envelope, right? Because one of the things you'll quickly learn in physics is what you really need to do is be able to back of the envelope estimate many things to see, do I need to do a concrete calculation of this effect or not? And so I'm going to show you how to do a back of the envelope calculation of the axion mass, or axion abundance in nature. And it turns out to give answers within a factor of 3 or 4 of proper calculations. All right. So I'm not sure how much you guys got in cosmology. So I'm just going to go over very quickly, how does a scalar field with just a mass term behave cosmologically speaking? So what's the equation of motion of a scalar in sort of an FRW universe? I'm going to call the scalar A for obvious reasons, but it's going to be the FRW equations are m squared. So here, what we're doing, so we are going to appeal to inflation in some sense and say that inflation makes the entire universe homogeneous, right? That was the thing, problem it was meant to solve. And so we're going to assume the axion field, again, is homogeneous in space. And so we only care about the time derivatives. And so we're looking at, this here is just the FRW equation for your Axion. And if you look at it for a moment, you'll realize this is a very familiar equation. It's called the harmonic oscillator with a damping term. So if you think back to classical mechanics, what happens if this damping term is large? Then you have an overdamped harmonic oscillator, and A essentially stays in place. A will be, because A dot will be small, you can neglect this term, and you can say that delta A is approximately m squared, whatever value of A you are at, over 3h times T. And if your friction force is large, your change in the axion is very small. So if you're looking at, let's here have just time. If you're looking at times when Hubble is much larger than the mass, then A is just a constant. Let's just call it A0. It's essentially frozen in position. Now, let's go to the other limit, where the friction term is very small. In that limit, we have an underdamped harmonic oscillator. And what happens is A behaves just like, this is going to be annoying. Did not think this through. Okay, an underdamped harmonic oscillator is A goes as A naught cosine omega t, or MAT. And so this is obviously the standard underdamped harmonic oscillator. And then you say, well, now let's include the lowest order effects of the friction term. So the early universe turns out to be radiation dominated. And so Hubble, we're going to put in radiation domination. So Hubble, we're going to scale as 1 over 2t. So you can solve this equation for A with a friction force that's decreasing with time. And what you see is that this equation is just modified to MAT to the 3/2. So in the early universe, you can see that A naught is a constant. So this is for, this is the case for Hubble much less than MA. And we had the case if Hubble is much larger than MA, that A just scales as A naught. Now, this has a very nice interpretation, because this means that if Hubble is large, your scalar field behaves just like a CC, right? It's not changing in time. You have a potential. The kinetic energy is 0, right, because it's a constant. The potential is just some value, and so it's some CC. It's just sitting there being a constant. Once you transition to Hubble being less than the mass, it looks like it behaves like this, which has a very nice interpretation, because this, if you remember what radiation domination looks like, your scale factor, which people usually also call A, let's just call it scale. Your scale factor scales as square root. People are not going to be able to see this. Okay, let's do that. That's one of the, R scales as square root of time. Your scale factor is square root of time. And so you'll notice that this is essentially A naught times R naught over R of t cubed. 3/2. Sorry. Wait. I am messing something up here, I think. But yeah. So what you're getting is that it is your axion is going to be diluting away like matter. And so this is sort of the physical intuition of an oscillating scalar field, is that if you have a scalar field oscillating, it's just a bunch of particles at rest. And so this is very different from other production mechanisms of particles. Why is that? It's because normally when you produce particles, like I guess you're going to hear a lot about it next week, and then you heard a little bit before, particles are produced at the temperature T of the standard model bath. And this means that you can't make dark matter very light because essentially you run into hot dark matter constraints. However, axion masses, for example, are micro EV. But if you produce them by this mechanism, which is called the misalignment mechanism, they're naturally produced very, very cold. And thus, you don't run into problems with hot dark matter. And so, in fact, this is basically by far the best mechanism of producing dark matter which has light masses. Okay, and so that's all nice and good. So let's basically use just these two estimates here to estimate the number abundance of axions. We will literally say if H is not just much, much greater than, if H is just greater than MA, we'll use this approximation. And if H is less than MA, we'll use that approximation. Okay.
So can you see just from this that they're very cold?
It's essentially what matters for them being very cold is this thing. In particular, you'll notice it's oscillating with a frequency MA. Essentially, it's because the mass term here is just MA. And how do you see what's the energy of a system, right? It's the Fourier transform with respect to time. And cosine MA has a delta function at MA. And so this means the energy of the particles is MA. And so that's how you see that it's literally just a cold particle with zero of everything else. Is it sitting with just at rest entirely. Okay, any other questions? Let's move on to the next board. So I'm going to first go over how you do this estimate. Slightly wrong, but it's actually the way most people describe it. And in fact, it is completely correct for particles which are not the axion. Let's put a line here. So what you do is you first, let's look at my notes. So basically, this mechanism is completely independent of whether or not this particle solves the strong CP problem. It's just a light scalar. And so this works for anything which is just a light scalar. And the difference of why it doesn't quite work for the axion is the axion mass has some pretty strong temperature dependence. Whereas a lot of the times when people are talking about this just in the context of dark matter, their mass will have a very weak temperature dependence, and you can completely neglect it. So we're going to first calculate it, assuming that the mass is a constant in time. And then you'll get an answer, and which works for any particle, which is basically just a particle with a light scalar with a mass, and whose mass does not depend with temperature. And then we'll go to the temperature-dependent case, which is the case for the axion. Right? Okay. So in the first time, you have Hubble much larger than the mass of the particle, and V is going to be basically just m squared a naught squared. Right? It has some initial value, the energy. So I'm going to be doing everything back of the envelope. So the fact that like factors of 2 and whatnot, I'm just going to be completely neglecting, which is why I'm not putting a factor of 1/2 there. So you first have an energy, and it's completely constant until you get a time Hubble of order the mass. And then at this point, your energy in your axion, I guess I called it V here, but I'm just calling it, the energy is usually people write as rho, will scale as m squared a naught squared times r naught over of t cubed. And so at this point, you just say, when Hubble is of order m, this means the temperature of the standard model, right? Hubble squared is the total energy, rho total, this is rho A, over m Planck squared. I'm ignoring factors of 3 and 8 pi squareds. And so this is temperature of the standard model to the fourth over m Planck squared. And so this means that rho standard model is m Planck squared times m squared. So you have rho Sm equals m squared m Planck squared. Let's put a comma here so you can tell they're separate. And so now you just say, we know the dark matter abundance. The easiest way to say that, let's see. So at least the trick that I use, everyone has their own trick, is to say that at high temperatures, to get the right number abundance, you need rho is basically GeV 10 to the minus 10 t cubed. So the way there are several ways to get to this equation. To get rho dark matter, as long as dark matter is non-relativistic. So what I remember is basically that the abundance of baryons is 10 to the minus 10. In other words, it's 10 to the minus 10 times the number density of photons, which is t cubed, and it has a mass of a GeV. Another way of doing this is that basically you want matter radiation equality to happen around an EV. And that's why basically GeV times this 10 to the minus 10 is roughly an EV. And because I'm forgetting order 1 numbers, that's why they aren't exactly the same. So what you see then is you just say, you set rho dark matter equals 10 to the minus 10 GeV t cubed. We know what t is, of the standard model is here. So this is GeV 10 to the minus 10 t is that. So it's going to be m Planck m of your particle to the 3 halves. And this is equal to m squared a naught squared. And so this means that basically you just solve this equation for any given mass. There's one particular value of A0 that gives you the correct abundance. So if you're interested in just in light dark matter, this is basically the equation you need. Normally, people will say, what's the natural value for the expectation value of A0? Well, at least in the case of the Axion, and usually in the case of these guys, it's a compact field. All right, it's e to the I, A over F. And so a natural value is to say it's of order F. Because it's the field range of A goes from 0 to 2 pi F. And so you say a random point is just here. It's some value, let's say pi times F or something like that. So this is usually scales as m squared F squared. And then you just say, I want to have a dark matter that has some particular mass. Let's say it's fuzzy dark matter. It's 10 to the minus 20 EV. Then you can calculate what F has to be in order to get that number abundance. Okay.
Sorry. What's rho A in terms of the field A? And the analytic expression?
In terms of, so rho A is just 1/2 m squared A squared plus 1/2 A dot squared.
Because you wrote A depends like t to the minus 3 halves, or like A squared like
Yeah.
r to the minus 3. So if it depends like A squared, that would be r to the minus 3.
Yeah, so that's part of the reason why I think I messed up a number over there, that it should be 3 halves.
Right.
Because the energy density is what scales as
That's right.
r over r
So
cubed.
you're saying the solution then is,
Yeah, so I think I messed, that should be to the 1/4 power. This is what I get for not consulting my notes when writing equations. Yeah, sorry about that. Yeah.
So could you just repeat, what was the deal with setting rho standard model equal to m squared in the Composite there?
The statement is just when Hubble equals m, now I can start treating this guy like cold dark matter. But then what is the temperature of the standard model at this point? Well, the standard model is what determines what Hubble is. And so Hubble is just t to the 4th over m Planck squared. And so I'm just calculating what is the temperature of the standard model when the axion starts behaving like cold dark matter.
I see. And then we can assume that, yeah, so it makes sense that the standard model has all the energy density because these axions are like super light and super cold, so they don't.
Yeah, that's right. And because we're trying to make it dark matter, and dark matter is the subdominant energy component in the early universe. So it's possible that this could have been the entire energy density of the universe, but then it's not dark matter. And so because we have this, we're aiming to make it dark matter. Yeah. Okay, so let's retell this story now for the QCD axion and figure out how to tell what the axion potential is. And so let's redo this story now. So as I mentioned before, people like taking A naught to be F. So let's put this F squared. M squared of T. And so we're going to, I'll actually describe a little bit later how to do it, but let's just see how does the mass of the axion depend with temperature. And the statement is MA of T is, if this is T 0 infinity, it's just an increasing function. So that's all we're going to use about the axion mass for now. It's an increasing function with as temperature goes down. So as the universe gets colder and colder, the axion mass increases. Okay, so our starting point is going to be when Hubble is of order, well, maybe I can just use, excellent, is when Hubble equals m squared. Hubble scales is m of T. And remember, Hubble is T squared over m Planck, which is why this equation has one solution. Okay, so there's some temperature, let's call it T critical, when the Hubble mass is equal to the axion mass. So at this point, what is the energy density in axions? Rho A is m squared of T times F squared. However, because m is increasing, this is not the quantity we're actually that's most useful to us. So what's most useful to us is actually the number density. The number density of particles is the mass times F squared. So the reason why this is important is because in the case of the axion, it turns out that at this point, m dot is much less than m squared of T critical. So in other words, the slow change in the axion mass is adiabatic. So in other words, we can use the WKB approximation, which is that as the mass is increasing, the energy is changing, yes, but the number density of axions is constant. And so that's why we care about the number density and not the energy density. Because if we just forget about the expansion of the universe part, what is constant in time is the number density and not the energy density. And so what we use, So then we have to wait until we can use energy conservation, right? Because the mass is changing, so the energy in the axions is changing. And so at some point, you'll have a new part where m equals a constant. And that's when you can start using the energy density. Because what we've measured in dark matter is the energy density, not the number density. And so while the number density is important to track while the mass is increasing, when the mass stops increasing, we need the energy density because that's what we've measured about dark matter. We have not measured the dark matter number density.
We expect M dot to go like H times M.
So the reason why, so it scales is roughly h times m. And because h has a 1 over m Planck in it, this very quickly shrinks, is less important. So literally right at h of order mt, this is more like a sim. But very quickly you just reach the adiabatic constraint. And so because I'm being so sloppy about what happens right at h of order m, I'm sort of throwing that into the slop, which is order 1 numbers. And so if you want to do this correctly, you have to sort of just, what people do is just literally just solve that differential equation with the time varying mass. But we want to do an order of magnitude estimate, so we're going to do an order of magnitude estimate first. Yeah.
I'm a little bit confused. So like, I think also Luke asked this question a little while ago, but the thing about basically that axion abundance starts off as like cold dark matter. But then are we assuming that like it's thermalized with the standard model here? Or?
No. So in fact, it is terrible if it thermalizes.
So
because the energy approaches the temperature, and then it becomes hot dark matter.
Yeah, great. So then why are we thinking of M as a function of?
It is because, so here's, it's essentially because if temperatures are larger than a QCD, the QCD scale, QCD does not confine. You're in a deconfined phase. And the entire calculation of the mass of the axion assumed you are in a deconfined phase, in a confined phase. And so that calculation is just wrong. So it's essentially the statement that if your temperature is above a GeV, you shouldn't be talking about pions. You have to be talking about quarks. And so that's essentially the reason, is that it's just we did a t equals 0 computation there, and the temperature at which it breaks down is of order your UV cutoff, which is like 100 MeV, or 4 pi 100 MeV. And so if you're at temperatures larger than a GeV or so, you can't use the chiral perturbation theory calculation, just because you're using the wrong degrees of freedom.
So even though the axions aren't thermalized with the standard model,
it's mass.
They know about when the bath goes through.
Yeah, that's right. Mm-hmm. Yeah. All right. So let's estimate. Let's see. I guess I have a short amount of time. What is the mass dependence of the QCD axion? How does it depend on temperature? To do this, I'm just going to claim a few things about instantons that I did not describe. Because when I talked about instantons, I did it in a theory without quarks. And instantons, when you add in quarks, you have things like zero modes that end up appearing, and I didn't even talk about those. So what I'm going to claim is that when you do instantons for QCD, not the Yang-Mills example I gave before, what happens is you have your instanton, and which is just some blob where some stuff happens. And coming out of it are now your U conjugate, one of each type of quark, D conjugate, strange conjugate. I I don't have time to go into the details for why this happens. There are some very nice index theorems that show how these things occur. But you'll just have to trust me that when you do it, for QCD, what happens is you don't just get the blob by itself that evaluates to something. You get quarks coming out of it. I guess Jim went over ailerons very quickly, so it's very analogous to that where you have quarks coming out. Okay, and so your potential for the axion scales like this. And now I have to get rid of all these fermions. So because I'm interested at temperatures of order the confinement scale, around GeV, around 100 MeV, I'm just going to close these loops with mass insertions. So there's an MU, MD, MS. And so this number is MU, MD, MS. Your potential, your energy, right, has dimension 4. So the only other scale in this problem is your temperature here. So by dimensional analysis, it has to scale like that. And as I mentioned before, instantons have this exponential suppression there. So it is also exponentially suppressed with e to the minus 8 pi squared over g squared evaluated at the temperature. Right? The RG scale is going to be the temperature. Now, this guy, if you put in the one loop running for your G, is confinement scale over T to the beta function, which is 11/3 number of colors minus 2/3 number of flavors. So this gives MU, MD, MS, lambda to the 11 minus 2 is 9. Is that right? Yes. Over temperature to the 8th. And so this is sort of the leading order estimate for how the, and then there's a plus I theta here. So this actually is a mass term that I didn't write. You have cosine A over F plus theta bar here. All right. And so this generates a mass term for the axion that's temperature dependent. And this is the instanton estimation, how you order of magnitude do the instanton estimate for the mass of the axion. Okay. We can now go back to here and actually start plugging in some numbers. Wait, running out of time here, so let's hurry very quickly. The first thing you do is you calculate what is this critical temperature. If you take the mass, right, the mass of the axion, m squared of t equals this guy here, mu, md, ms, confinement scale to the 9th, t to the 8th, f squared, right? You Taylor series this guy to 2 powers to the second order, and then the mass term is that term, and so your mass scales like this. And so you set this equal to t squared over m Planck. When you solve this, it turns out to have lots of ugly powers. So I'm just going to tell you the answer is that T critical is about 1 GeV and doesn't have strong dependencies on things like F. So then, okay, so that gives you T critical. And so then how does the number density dilute away once you've reached T critical? It dilutes like the scale factor cubed, right? Because the number density is conserved up to the fact that the universe is expanding, right? And so what's a constant is basically m of t critical f squared is equal to m of t at some other time f squared times r of t critical over r of t cubed. Okay. Okay, so then when does the Axion mass stop transforming? Well, let's see. Yeah. Okay. Let's just go over to this board. I have to go really fast, so I'm going to apologize and just skip a lot of math at this point. This is just how it goes, since I'm really out of time. The mass, the number density, right, is the co-moving number density is conserved, and so the number density is just diluting away. And eventually, right, you can see that you'll enter the chiral perturbation theory regime where at around 100 MeV, the Axion mass stops changing. And so what you do is you evolve from 1 GeV to 100 MeV, and just say at 100 MeV, I do the exact same estimate I did before here, which was that rho at 100 MeV of the dark matter should be equal to this number here, right? It's 10 to the minus 10 t cubed times GeV. And when you do this, you get that the Axion dark matter abundance is mapped when F is about 2 or 3 times 2 to 3 times 10 to the 11 GeV or so. And so this is the sort of instanton estimate for when you get dark matter axions. If you actually put in lattice results, instead of using this, you can take the lattice results to get the finite temperature axion mass. And when you do that, you get results that are slightly closer to 10 to the 12 GeV. But those are sort of, at the level of estimates I was doing, you don't trust this to up to an order of magnitude anyway. So getting within a factor of 3 or 4 is actually pretty good. Okay, so I guess my time is up. So hopefully I sort of briefly reviewed or covered how you estimate, just back of the envelope, the mass, the energy density of light scalar particles in this case. And if their mass term, it depends on temperature, like the axion, then you have to go through and do this adiabatic approximation. So that's one additional step. But it still ends up being sort of only 1 or 2 pages of algebra, and instead of like a year or 2 of like doing lattice calculations and working very hard. And you get basically the right answer. Okay, I guess that's it for now. Any questions?
So when you did chiral perturbation theory, action mass did not depend on MS.
Yes, that's right. Here I'm at temperatures larger than MS. So that's why it appears. And so there, if I took the 3 flavor model, the axion mass does depend on MS to some small extent. And it is sort of one of the slight embarrassments of instanton calculations that instantons always give you a cosine. And you'll notice that at low energy, it's not exactly a cosine. And so like this instanton approximation is just an approximation. It doesn't get everything. Like, for example, recently people have done lattice simulations of the axion mass, and I believe they got this temperature scaling is roughly about this, but then the absolute number out front happens to be something like 10 larger than what the instanton estimate is. And so really these instanton estimates are very just like back of the envelope to try to guide what you should expect. And they're really valid when T is much, much larger than the QCD scale, which is then it actually is proportional to MU, MD, MS, MB, MC, everything. And the way those things disappear is because when you integrate out the quarks, what you call the confinement scale changes slightly because the beta functions change slightly. And so that's really why these MSs appear here, but then if you go to temperatures below it, it looks like there's no MS. It's because it's been absorbed into what you call the confinement scale. Yeah.
Oh, sorry. I know you mentioned this, but I just missed it when you did it. Wait, where do we draw this diagram from again?
So this is the statement of when you evaluate the instanton background before, in the absence of QCD, well, in Yang-Mills, you got an n plus 1, n was not equal, or e to the, with your propagation here of e to the I h t is not 0. When you redo this calculation with quarks, you need to put in the operator UU bar, DD bar, SS bar to make it non-zero. So in other words, this operator also creates quarks, and so you need to create operators to get rid of those quarks, or you put in one of these states a state with no quarks and a state with quarks. And it's an annoying fact about doing the fermion path integrals.
Is that
It doesn't occur for bosons, for example.
Sorry, so you said you have to insert those in addition to like your normal.
In addition just to the field configuration to get a non-zero answer.
Is that obvious?
No. It is, I just did not have enough time to go over zero modes and instantons with flavors correctly.
So sorry, do you want equal number of quarks in the in and out states that are non-zero, or do you want unequal number?
You want, so you can have the in state having no quarks and the out state having 6 quarks, for example.
Okay.
That's, yeah.
Yeah, I have a quick question. If you approximate the temperature dependence of axion mass as a step function, but let's say at a very high temperature, does that mean there's no energy density?
So you'll notice that if you approximate it literally as a step function, then you go back to the first estimate I did where the mass, no, sorry, no, it's, so if you put it as a step function, what you do is you miss the fact that the number density is conserved and the energy density is not. And you actually get the wrong answer if you approximate it as a step function. You get it by like several orders of magnitude wrong. And so if you say MA equals 0 at high temperature and the 0 temperature value at the QCD scale and below, you get the wrong answer. In particular, you'll notice in that case, there's absolutely 0 F dependence. Because as soon as it starts oscillating.
Yeah, but there's an initial field value.
Yeah, there's the initial field value, yes.
But that also is dependent on M square F square A naught square.
Yeah.
A naught square is also dependent on F.
Yeah, so if you just treat the initial field configuration as, or field value as arbitrary, then if you do what you just said of a step function, you get no F dependence. Well, in particular, M squared F squared for the axion is M pi squared F pi squared. And so F just vanishes there. And so it cancels with the mass. And you get absolutely no dependence on the mass or the F of the axion. And that's, we know is not the correct thing. Because that would say the axion, no matter what F is, would give either the right abundance or the wrong abundance. Yeah.
Whenever you can you put up a source to this calculation, either on the wiki?
Sure. Yeah, there are not good references, but there are references. Yeah, I don't think there's like a very good review of axions in general that people point to. There are a few that are okay, but there's nothing like let's say like Daniel Bauman's TASI lectures or anything like that, right? There's no like go-to place which just tells you everything you need to know. Maybe. Right, any other questions? Yes, I will. I actually have scanned versions of the second and third lectures, and so I can definitely put those up. The first lecture, I wrote a few wrong things in my notes, and so I don't want to put those up. But that's all in Trzedniki, the first one. So yeah, I'll do that. All right. Anything else? Excellent.